Hello, chemistry students, and welcome to another lesson on acids and bases. We're going to talk about a few different things today. First, we're going to talk about some different models of acids and bases, and these should be familiar to you, but we'll just present them once again, ways that we think about defining an acid and a base. We're also going to talk about strengths of acids and strengths of bases. Why is it that we think of hydrochloric acid as being a strong acid? It's not just because it's in some concentrated form. We've been talking about molarity and the concentrations of solutions. Why do we think of some acids as generally being strong acids and some acids as being weak? What is the reason for that? So we're also going to talk about water and some of its unique properties regarding acids and bases. So let's get started. So let's look at one model of how we think of acids and bases. It was provided to us by a man named Svante Arrhenius. He was a Swedish scientist who worked a lot with electrolytes and came up with this idea that acids produce hydrogen ions in an aqueous solution. This was probably late 1800s, so it wasn't really all that long ago. He said then conversely, bases produce hydroxide ions in aqueous solution. Now you've heard this definition. We've already been working with it somewhat. Here are just some examples. Hydrochloric acid is producing a hydrogen ion or a proton, so it is an acid. Here we have sodium hydroxide. It's furnishing this hydroxide ion, so it's a base. The problem with this definition is it's kind of limited. We can only have one kind of base, one that has a hydroxide ion. So let's look at another model. So in the early 1900s, a couple of scientists, a Danish chemist named Johan Bronsted, and that's where we get the Bronsted part of this, and an English chemist named Thomas Lowry came up with another model, another way of thinking about acids and bases, and we call it the Bronsted-Lowry model. And that is when an acid is defined as a proton donor, and the base is defined as a proton acceptor. So this is a little bit different. Obviously, we can now have bases that don't have to have a hydroxide ion in them. And the reaction occurs when the acid's dissolved in water. We can represent Bronsted-Lowry acids by HA, A meaning the anion in the acid, H obviously the proton, the hydrogen. Here is just a general Bronsted-Lowry acid-base equilibrium in aqueous solutions. We're going to talk about what this means. Conjugate acid, what is that? A new word. But here we have this acid and water, and the acid is donating its proton to the water. Consequently, the water is considered a base because it's accepting the proton. So let's look a little bit more at this type of reaction and define these conjugate acid-base pair ideas. So the conjugate acid-base pair consists of two substances that are related to each other by the donating and the accepting of a single proton. So if we look first at the base, water's a base because it is accepting a proton. When we go from here to here, water accepts a proton. So water is considered a base, and this hydronium ion is its conjugate acid. When we look at the acid right here, this is an acid because it's donating that proton when we go from here to here. We take our reaction going from left to right, from here to here, excuse me. It donated its proton. And what is left over is the conjugate base. So here is the acid and the conjugate base. Here is the base and its conjugate acid. And they are related because they are related by the donating and donating and accepting of a single proton. If you're confused about, determining what the conjugate is, when we have an acid, we will always have a conjugate base. And when you look at the acid, you can see that it can donate a proton. Its conjugate base then will have the ability to accept a proton. And same here, we know that water is a base because it's going to accept a proton, has the ability to accept a proton when it goes from here to here. When we look at this ion, we can see that it's going to be the conjugate acid because it has the ability to donate a proton now and to go in reverse. And let's take a look at that forward and reverse ability of this reaction. Here is just a rewriting of what we just stated. We have our acid, our hydrochloric acid. It's donating that proton to the water, the H2O. And because of that, this is the acid, this is the base. The conjugate acid is right here. The conjugate base is right here, the chloride ion. And that's how those are paired. So, remember I just said we can have this reaction go in reverse. That seems kind of strange maybe, but that is indeed what can happen. We have this acid right here, HA, this base, water. It's forming the hydronium ion, and it's forming the conjugate base, the anion. We can take these products, the conjugate acid and the conjugate base, and they can react with each other. So here's the conjugate base. Here, I'll draw that in the same order. So there's our conjugate acid and our conjugate base. When they react together, that conjugate base accepts a proton from the water and makes HA. The water, or the hydronium ion, donates the hydrogen, right? It's then therefore going to be H2O. And wow, we get the exact same things that we started with. Indeed, this happens. The reaction can go both ways. We usually represent reactions that can occur in both directions by double arrows, like this. So I would actually write the reaction with arrows going both ways, like that. So now that we know this reaction can go in both directions, we need to talk a little bit about what direction the reaction tends to favor, the predominant direction of the reaction, because that's going to make a difference in how we write the arrows. The predominant direction that the reaction occurs will have a longer arrow than the other direction. And let's talk a little bit about that because it has a lot of different implications. It tells us a lot about the strength of the acid, depending on which direction wins out, which direction is favored in the reaction. So if, for example, here's our water. If water has a very high attraction to the proton here, compared to the anion right there, then the acid, the HA, is completely ionized. It means it dissociates completely in water. And HA is considered a strong acid. So that would mean if HA is a strong acid and the water is highly attracted to that proton over the anion, the reaction is going to proceed this direction much stronger than in this opposite to the left direction. And so if HA is a strong acid, we are going to write an arrow that is longer going to the right because it is going to favor that direction in our reaction. In essence, the water wins out over the chloride anion in attracting the proton. And because the water wins out, we favor these being formed rather than the reverse reaction happening. So in this case, here's an example of a real live acid rather than just this HA theoretical acid. Here's hydrochloric acid. And that is exactly what's happening. The water does win out in attracting the proton, and hydrochloric acid dissociates nearly completely in the water. And the reaction proceeds to the right, and we consider hydrochloric acid a strong acid. So I've just said a couple of things here about the strength of an acid. An acid is considered a strong acid when it completely dissociates in the water. So that is another way that we talk about it. They're interrelated, but another way that we talk about the strength of an acid has to do with the degree of dissociation in water. Here is a strong acid, HA, and when it's put into water, we get almost entirely protons and anions dissociating. See how they're all separate here when we put that into the water? Here is another acid. We'll call it HB. It's a weak acid, because when we put HB into water, we still have a lot of HB in the water. See, here's our HB. The proton is the little white, and then the B would represent the anion. When that was put into water, we still have a lot of them stuck together, bonded together. And we have very few protons, and here's a proton and an anion floating about and dissociating in the water. This would be considered a very weak acid. So let's take that idea of dissociating in water, and let's look at another angle to that idea. You know that sodium chloride, NaCl, that's table salt, right? It is a salt. When we put that into water, we have an excellent conductor of electricity. Isn't that interesting? An excellent conductor of electricity, if something's an excellent conductor, it is called a strong electrolyte by definition. And the reason it's a strong electrolyte is because the sodium and the chloride ions completely separate. We get almost entirely sodium ions and chloride ions floating about in there. They separate completely, and we have a lot of ions that can conduct electricity and that an electric current can be run through. So, lo and behold, might shock you, but HCl is also a strong electrolyte. When that is dissolved into water, it produces, remember we said that's a strong acid, it dissociates almost completely. And so it's also a strong electrolyte. So things that are strong electrolytes would be salts, we already knew that, strong acids and strong bases because of the property and by definition, a strong acid and a strong base, when it's put into water, will almost completely dissociate. Weak electrolytes would be weak acids and weak bases because they do not dissociate very much. They have some weak electrolytic properties. Let's look at the relationship between acid strength and conjugate base strength. Here is a little diagram showing acids and bases. If we look at the acids, we have strong acids are down here at the bottom, really, really strong, and they get weaker as we go up. Bases are the opposite. We're starting up here with the strong bases, and we're getting weaker as we go down. So let's look at the strong acid, hydrobromic acid. Very strong. When you put it in water, it almost completely dissociates into its respective ions. The conjugate base of this strong acid would just be bromide, right? Because when hydrogen bromide gives up its proton, when hydrobromic acid gives the proton up in aqueous solution, we're left with a bromide ion, and that is the conjugate base. It is a very weak conjugate base. So a strong conjugate acid produces a weak conjugate base. And you can tell that it's sort of a gradual process as you decrease in the strength of your acid, your strength of the conjugate base increases. So that is the relationship between acids and conjugate bases, or between bases and their conjugate acids. Also works in reverse. That weak base has a very low attraction for the proton compared to water. Remember, that's what we mean also by a weak base. So let's review what we've talked about so far, different ways that we can describe acid and base strength. We can look at acid ionization reaction, the dissociation of it, how much is that acid able to dissociate? How much is it completely ionizing or not? Very much related to that would be the strength of that acid as an electrolyte, because obviously if it's dissociating to a high degree, it's also a strong electrolyte. The forward or reverse reaction, which one predominates? Is the reaction proceeding mostly to the right or mostly to the left? And we can tell acid strength by looking at the predominant direction of the way the reaction is going. We can also look at the strength of an acid's conjugate base compared to water, and that will tell us how strong an acid is. Now, what about water? We're talking about acids and bases here. What about water? You've seen water behaving as a base in one of our examples. It can accept a proton. We're talking about Bronsted-Lowry acids and bases, obviously. But you know, water can also act as an acid. It can lose a proton too. Isn't that strange? Water is what we call amphoteric. It can behave as either an acid or a base. Here is just an example showing the ionization of water. We have water and water. It's creating hydronium ions plus hydroxide ions. And in this reaction, the vast majority of the water, though, remains as H2O. Only about 1 water molecule in 500 million is ionized. So there's really very little of this. The reaction is primarily and predominantly to the left. This is not written very accurately. I just got that off of the internet. This is a nice little format, a little bit better than some of the formatting I do, but the arrow should really lean more heavily to the left. Okay, so here we have it rewritten correctly with the reaction proceeding predominantly to the left. And let's talk about this reaction a little bit. It's a really interesting reaction, and I'm going to introduce one last concept to you. And it's a very important one, and it will be one that you can use to calculate concentrations of different ions in the water. Water, when it is dissociating into these ions, we know that the hydronium and the hydroxide ions are going to be equal to each other. Their concentrations will be equal to each other. That would be the same thing as saying the proton ions is going to be equal to the hydroxide ions. Sometimes you'll see the hydronium just shortened into a proton. So there is this idea called ion product constant for water. We designated that by a capital K with a little W that goes down subscript below it. And the definition of this is it's a product, the ion product constant. So we're going to look at the concentration of both ions, the proton and the hydroxide ion, and we are going to take the product of that. So we'll multiply the hydrogen ion concentration by the hydroxide ion concentration. That's the product part, ion product. Okay, so we're multiplying the concentrations of the two ions together, and that always produces a constant. And that constant is called Kw, the ion product constant for water. That's how we abbreviate it with the capital K, little w after it, and it's constant. It means it's always that. Whenever, no matter what is contained in our water solution, no matter what we have, the constant is always 1.0 times 10 to the negative 14th when we're at 25 degrees Celsius. If we start changing temperature, we're going to have something different for that. It will not be the same. But when we're looking at room temperature, which is usually, we consider room temperature to be 25 degrees C, our ion product constant for water, Kw, always equals 1.0 times 10 to the negative 14th, no matter what is contained in solution. Why do we care about that? Why is that important? Let's look at what the ramifications of that are and what it allows us to be able to calculate. In a neutral solution, these will be equal. the protons and the concentration of protons and the concentration of the hydroxide ions, those will be equal. In an acidic solution, if we put some acid in our water, we will end up with disturbing this balance, right? Because in all cases, we know the concentration of hydrogen ions and times the concentration of hydroxide ions always equals the same number. So if we pour in extra protons in there, this will be a higher number, that will go up, and this will drop. It will decrease because this is always the same. So in an acidic solution, the hydrogen ion concentration will always be greater than the hydroxide ion concentration. Also, in a basic solution, the hydroxide ion concentration will always be greater than the hydrogen ion concentration, because we know that in all cases, the product of those is going to be equal to 1 times 10 to the negative 14th. It will be a constant. So let's use some of that information and look at a problem. If we have a solution that contains 1 times 10 to the negative 5th molar hydroxide ions, we're asked to calculate the concentration of hydrogen ions and hydroxide ions. We don't actually need to calculate that because we're given it at 25 degrees C. Now, when we talk about kW, we're talking about 25 degrees C. If we alter the temperature, if we do something different for the temperature, then that constant is not the same. It does not hold. It is only true for 25 degrees C, room temperature, and that's it. So we're going to do this at 25 degrees C, and then we're asked to decide if this solution is neutral, acidic, or basic. So let's do that. Let's take our kW equals the product of the hydrogen ion concentration and hydroxide ion concentration, which equals 1 times 10 to the negative 14th. We can find the concentration of our hydrogen ions by simply plugging values into this equation. So I'm going to take hydrogen ion concentration and just rewrite it here. I'm going to plug in the value of my hydroxide ion concentration, which I get from my problem. It's 1 times 10 to the negative 5th molar. I'm going to plug that in, multiply them together. That's equal to 1 times 10 to the negative 14th. I'm going to rearrange this a little bit. If I divide both sides of my equation by 1 times 10 to the negative 5th molar, then I can cancel these out on the left side. And when I rewrite that, I get the hydrogen ion concentration equals 1 times 10 to the negative 14th, I'm rewriting there, divided by 1 times 10 to the negative 5th. I divided both sides by 1 times 10 to the negative 5th. Now, if you'll remember, just a quick review, when I am dividing exponents like this, 10 to the negative 14th divided by 10 to the negative 5th is the same as 10 to the negative 14th minus a negative 5th, or 10 to the negative 14th plus 5. So it would be 1 times 10 to the negative 9th molar, and that would be my hydrogen ion concentration. Remember, my hydroxide ion concentration is up here. When I compare those, notice this is 10 to the negative 9th. This is 10 to the negative 5th. This is going, the decimal place is going far, far, far to the left, much farther than this one is. So this number is much smaller. So when we write this inequality, my hydroxide ion concentration is much greater than my hydrogen ion concentration. And remember that that is a basic solution. So just to review, we've talked about two different models for looking at acids and bases, the Arrhenius's model and the Bronsted-Lowry model. We talked about acid strength and how we determine if it's a strong acid. What does that mean? A lot of different ideas surrounding that. You need to make sure you understand the different ways of knowing if it's a strong acid or a weak acid. We've talked about water, the ionization of water, and the ion product constant. It's our last big hurrah in this video. The kW, the ion product constant. It's always constant. There are some There's a worksheet that has some problems that you can do to show your proficiency for all of this. So it's a lot of, I know it's a lot of information all in one video. Here is another advanced idea. Feel free to look through that, see if you can do some explaining. If you can figure out this little problem, I'd love to hear your ideas and your thoughts, and I'll see you in class.